Hi everyone, and welcome to today's session on Introduction to Agents. So agents have been a very popular topic recently. It is about cognitive agents that can navigate, that can explore and act on the world. And these agents are fundamentally powered by this new trend called the large language models. Actually, not that new. It's been 5 over years already. But this is something that is quite interesting because for the first time, we can actually see how an AI system can think. And you can actually see this because you can ask the AI system why you are doing such things. Okay, how can we incorporate all of this into a functional agent? So let me start off with a story. So look at this cute little robot here. This is your agent, all right? This agent is primarily consisting of your large language model. And the large language model, as you already know, does stuff like fill up the next token. Like, for example, the cat sat on the, and based on the training data, it might fill up the next one, maths. Okay, how is it able to do something so good? Okay, the main reason why it can do so well, there's two reasons. The one reason is that each of these words, or actually subwords, or you can call them tokens, each of these tokens, okay, encompasses a vector embedding. So these are like some meaning of what the token is. And by paying attention to, like, for example, if you are trying to predict this word here, you pay attention to all the previous words, all the previous tokens, and you can try to group the embedding vectors together to form a new embedding vector in order to predict what comes next. So like over here, you might pay more attention to like the word cat, okay? And then from cats, and then action set, okay, maybe you will know that it's like math. All right, so this is a very wonderful thing called self-attention, okay, where based on like the query. So in this case, the query itself is actually the last word here. The last token here is the, and then you from this, you query all the previous tokens and see what matches more. And based on what matches more, you adjust the meaning accordingly. It helps you to better predict what comes next. So this attention is really quite a breakthrough. And this has led to a lot of very good performance on a lot of benchmarks, especially natural language processing benchmarks. So is this all that a large language model can do? All right, apparently it's not very good at stuff like math. All right, so one of the earlier versions of the model, okay, not ChatGPT right now, but maybe GPT-2, if you give it a question like this, you have 4 marbles, John has 4 marbles, Mary has 3 balls. John gave Mary 2 marbles. How many marbles does Mary have? Okay, the GPT may not even understand how to solve it. Okay, they might output some gibberish. Okay, like, are you sure? What are you talking about? I have no idea, because this is something that is, you involve some calculation. It's not that obvious about how to do the next token prediction. So how can we solve this? So this mysterious man, anyone want to guess who is this person? Have you all seen him before? Okay, so for those of you who don't know, he's actually Morpheus from the Matrix. So I put him here because he's the one that will be training our agent today. Okay, and we basically ask, like, maybe instead of just going directly from the input to the output, maybe it's too complicated. You need to do the thinking in simple steps so as to guide the way to think. Like for humans, if you ask me to like plan how to how to create food for the world, that's a bit too ambitious. Okay, but if you break down step by step, you might ask like, how is food grown? How can we increase the output? How can we distribute? You can think through step by step, and it will probably lead to a better answer. So surprisingly, for large language models, you can ask it to think step by step, and it can give a better answer. So we just ask it to think step by step now. And now we can see that, okay, it's able to now come up with an answer. So this actually is the output from ChatGPT, okay, the most recent one. So it made this mistake, right? It's able to think step by step now, right? This robot is saying, yeah, Mary start with 3 balls, all right? Mary receives 2 marbles from John. So Mary now has 3 plus 2 equals to 5. All right, so it thought through step by step, but it's still making an error. And what's this error? Okay, the error is that it confused these balls for marbles. So you can go try it on ChatGPT. It still fails at this, I believe. So maybe what we need to do, other than just thinking through step by step, we also need to reflect and reflect upon what went wrong in our answer. So this reflection, okay, can come externally or can come from a human evaluator. Okay, in this case, right, I told it directly, balls are not marbles. Reflect and correct your answer, right? So this reflection caused it to think again and then starts saying that, oh, Mary had 0 marbles and received 2 from John. So Mary has 0 plus 2 equals to 4. Over here, I intentionally made a mistake here for the calculation to illustrate something later on. But if you ask it to reflect, okay, ChatGPT would solve the problem already. Okay, but now let's assume, all right, that it cannot do calculations that well, which is a fair assumption because GPT really has issues with calculation. You ask it to multiply some numbers, add some numbers, it may not be able to do it that well because these tokens here are not explicitly trained on this kind of calculations. They are not meant to be consistent. They are just pattern matches to see how to match the input tokens to the output tokens. So yeah, it gets it wrong here. So if we just naively use a large language model like that, we may not be able to get the right answers for this kind of specialized tasks that require consistency. This is a calculation task. You can easily imagine something like this for a memory retrieval task from a database. It might also get it wrong because consistency is not something that the large language model is specifically trained for. It is just trying to do pattern matching of the token distribution based on the input tokens. All right, so how can we improve this? All right, so again, our mysterious man here says, maybe we should use some specialized tools. Large language models maybe can't do everything well. Maybe this kind of calculation, you should use a tool. So how can we use a tool? How can we make this tool use part of the large language model process? So, all right, we do have 2 tools right now. The inner voice tells the robot, all right, tells the AI. You have 2 tools right now. Your first tool is a calculator tool, and you use it for adding numbers. Okay, over here is a simple one that you add 2 numbers. You take in 2 numbers and you output the sum of them. I mean, the tool will output it. You also have an image generator, and you can input a text prompt, and the output will be an image. You can ask the AI, what tool would you like to use? Oh, that's quite interesting, right? Like, I'm just a next token predictor, but now I'm asking the next token predictor to predict what tool is good to use, right? That's quite mind-blowing, don't you think? Like, you can frame a lot of things as a next token prediction task, and tool use can be framed as a next token predictor task as well if you give it the right context for tools. So this is my context. This is our context that we give the language model for the tools. Oh, I read 2W, but actually it's tools. So now we get the answer, the calculator tool. All right, but we don't have it. Okay, we don't have the inputs for the tools. All right, so how? Okay, so it did halfway, right? So I just got a chat. Chicken said you tried this on ChatGPT, passed the first time, but failed when I asked it to reconfirm. Okay, so let me just take a look. Okay, so basically the GPT gives erratic output, right? So this is the same thing that the large language models are kind of bad at, right? They don't give very consistent output. So that's why we introduce tool use. All right, hang on for a while. Too many windows, right? Now, let me just clear the screen. Okay. All right, so let's move on. The next thing that I'm going to talk about is how are we going to get the inputs for the tools? Right now, we ask it, which tool would you like to use? And, it just responds calculator. How are we going to get the exact things that we need to call this tool? So maybe what we need to do is ask it for the inputs, right? The mysterious man said, just ask for the inputs. What's so difficult, right? Okay, so let's ask for the inputs. So we ask it, what are the inputs for this calculator tool? And then The AI replies, okay, we want 0 and 2. Yes, it's based on this input context here. So that's great. We may be able to use this tool to get something useful. All right, but this whole process is a little cumbersome. Like, it gives us like a tool, and then we still need to ask for the inputs. And maybe there's a way to get this whole process for tool use in a more structured way. Is there such a way? And it turns out that yes, there is. In fact, majority of the web's data is trained on JSON. So when models like ChatGPT are being trained, they are exposed to this thing called JSON, which is something like a Python dictionary. You have a label and you have the field. All right. So you can ask LLMs, large language models, to output in this kind of format. So you can just say answer this in JSON format. All right, with the name and what the description of what you want, and the name of the label and the description of what you want. So this is working pretty well. So I created a framework called Straight.json that exactly does that. You pass the large language model output in a JSON so that you can get very structured output. And this very structured output can help you to more reliably use the tool, because like now you can get both the name and the inputs in a more reliable format. Okay, rather than just passing through whatever the large language model outputs to you, which can be very verbose. A JSON helps to make it more concise, more targeted, and you can extract the relevant views as you want. Right? If you don't want to use strict JSON, there are other ways to do it. Okay, like for example, OpenAI functions. Yeah, in fact, LangChain also have their own way of doing this. Okay, to do this kind of tool use. Okay, so you can explore all this. But the idea is, if we can get the AI to give us something more structured, right, that will solve a lot of problems, especially when we want to introduce more and more complicated things into our agent. So after the tool is caught, it's like, okay, I caught for the calculator 2, I gave it input 0 and 2. Something's missing. The tool doesn't directly talk back to the large language model itself. You kind of need to tell the output of the tool back to the large language model itself, because the large language model has no idea, okay? When we call the calculator 2, let's say we call the calculator 2 here, the language model has no idea. Okay, LLM has no idea what the output is or what this process is. How are you going to get this to the LLM? And the answer is surprisingly simple. You just need to feed back the output back into the chain of conversation so far. So we need to discover the environment. And how do we do that? We just feed back, okay? The environment observation will be 2. You can just give it like the answer is 2 or something. The output from your tool use can be fed as a text back into the large language model. So at last, we get the final answer. Mary has 2 marbles. Well done AI. After using chain of thought processing, okay? So the chain of thought is let's think step by step. So you can think of it, after asking it to do chain of thought processing, think step by step, all right? Or just even prompting it, think about the problem. Just the word thought itself can also prime some idea of planning, of deliberation of what to do. Right? Then after planning, we ask it, what action should we take? What tool should we use? Right? What are the two inputs as well? So there's also some few, sometimes they have this thing called action input. Okay. So what are the tools to use? What are the inputs to this action? And then after we use the tool, we get back the environment feedback. So this is the observation. So this is actually the React framework. So it's called reasoning and acting. So it's quite a nice word, reasoning and acting. So together it's called React. So this is used more or less for every single tool use I've seen. All use the React method. And I quite like this thing a lot because it reminds me of the warfare cycle that I'm used to. Like observe, orient, decide, act. I mean, this is very, very similar to like how you would, look at the situation, think about it, okay, observe the situation, think about it, okay, and then use a tool. This is like use a tool, this is like think about it and observe and think about it. So it's very, very similar to this cycle. And there's one more thing that could be done, all right? If let's say the agent is not able to do it that well, you can ask it to reflect. Okay, we have done this earlier. So if we get like a wrong answer or something, you can sometimes ask, are you sure of your answer? Or like reflect upon your answer and correct any mistakes. Okay, sometimes it's because when you do this kind of stochastic generation, sometimes you make mistakes. But once you are given this prompt again to reflect upon the previous chunk of tokens, it might be possible to correct that mistake just by looking at the series of tokens and identifying where it's wrong. So I mean, in humans, it's the same thing. Sometimes I can blur out some sentences. I think it's correct at the moment. But once I look back at the transcribed sentences, I might say, actually, this doesn't make sense. So this is quite amazing because LLMs operate quite similarly to human thought in that we can reflect upon what has been said so far and correct. So this has been used in this thing called reflection. Okay, that you add a reflection as well. So, wow, not bad. So far, we have used the React framework and expanded the capabilities of this simple LLM agent to be able to think, use tools, all right, and do some limited form of planning. All right, so it looks like, is this more or less it for LLM agents? That's good enough for most use cases already, right? You can use any kind of tools. You just use the tools to augment your capabilities. Is this good enough? Do you think it's good enough? Let's pause here for a while. Do you think this is good enough? Is the LLM agent that we have trained has already gained the ability to use tools, to observe the environment, to reflect upon its processes? Is this good enough as an LLM agent? Maybe I just pause here for a while to hear your responses. You can type in the chat or you can talk. Okay, never mind. I'll get your inputs later. But this is not all that is, okay, because what if we ask it something like this? What was the initial question? Okay, so right now our AI agent, takes in the inputs and processes the input to the output, but it only like maybe remembers this last few threads, and then it's like, oh, what was the question that you were asking me for? I completely forgot because it's all the way at the front now. There's no reference. There's nothing in my earlier context tells me what is the question because I've lost it after all the long conversation so far. So this brings about a very important point. Maybe we need this thing called memory. All right, how are we going to code in this memory? So the most naive way of coding the memory is like this. Okay, imagine you have all the conversations so far. We start with the tasks. The John has 4 marbles and so on. Okay, we move on to all the way until we get the final query, which is what was the initial question. So we can actually store the entire history of the conversation and prompt it, say, this is the history. Then now this is the query. Answer it based on the history. You can do that. Okay, but do you see a problem here? If your conversation is going to be 1,000 different conversations long or 1,000 different to and fro inputs, it's going to be very, very long. And there's a limit to the amount of context length that an LM can take. So this can solve our problem because our problem is quite simple. Okay, we only have like, let's count 1, 2, 3, 4, 5, 6, 7, 8. Now we only have about 8 different kinds of previous conversation history. Right? If you actually run this longer, you're going to have a lot of context length in order to store everything. Okay, this cannot scale. So our mysterious man says, maybe we should have an external storage. We cannot just rely on storing all of this in the context. That won't work. Okay, maybe we need something bigger. And that's where we have this idea of short-term and long-term memory. Okay, it's not exactly the neuroscience thing, but the idea of short-term and long-term that people have come up with for LLMs are that short-term, you just take like maybe the past 4 conversation or past 5. Over here is past 4 conversations. You take that and you put that as context. And then in order to remember the longer parts of the conversation, like in human conversation, we don't really remember every single thing, but maybe we remember the broad scope, the gist of what has been talked about so far. So we can actually ask the large language model in a separate process to summarize what has gone on so far. So this is the ChatGPT summarization I got for the entire conversation, which is not too bad because it remembered the initial question as well in the summary. Okay, so long-term memory might lose out on certain things because when you summarize things, you lose out information. So there's also one other way we can do it, and that is using retrieving of similar contexts. So you can use all these things here, all these past contexts you can actually store inside a vector, an embedding vector. Okay, and then you can compare your embedding vector using cosine similarity. Compare with cosine similarity. Extract out nearest n vectors. You can do that, or you can simply just pass in the entire chunk of text and ask ChatGPT to rate similarity. Okay, so there are various ways to do this. Usually people use the cosine similarity because it's cheaper. All right, it's only like less than 1 cent in order to do one chunk, and you can use that vector again and again to compare cosine similarity with your query. Okay, and find out the more relevant messages, and this can be put into your context as well. So you can put all of these three as memory for your agent, right? That helps to alleviate some of the problems. It doesn't solve everything, but alleviates a lot of problems. And later, we will be discussing more about how else can we encode memory. Okay, I'm not too satisfied with just this approach of doing it, but this is what has been done so far. It works for some use cases. Right, so yeah, agent can use tools now. Our agent can use tools. Our agents can observe the tool output, the environment output. Our agent can store memory of the past and use it for decision making in the future. That sounds more and more like a human, isn't it? All right, but is one agent enough? All right. Can we do with more? Okay, so, all right. Large language models can be prompted quite flexibly. You can give it the role of what it is, like, for example, a computer programmer, a stock trader, CEO, the CTO of a chief executive officer and chief technical officer of a software company. You can give it these roles. You can give it its own unique memory, unique tools for each of these agents. Okay, you can even fill short some examples of what to do for various scenarios. And it's been shown that you can actually flexibly condition your large language model agents to behave differently just based on this different initial prompts. And so we can actually have a lot of agents that do different things. This is starting to get interesting. Not just one agent, you can have many agents. Each of these agents have whatever React framework, reflection, memory, all this that we have talked about. And now this is one agent. Now we scale it up to many agents. Can we see something? Okay, then recently in this paper called Camel, okay, which is talking about how we can have a society of mind. And what the idea is, so far, all right, we have been doing the conversation where you have a user and you have an assistant, right? What if both the user and assistants are AIs? What if you can automate the user, right? So if let's say you're a computer programmer, you want to program something, you give it a meta task, like create a trading bot. Then it can interact with an assistant that is like a stock trader. All right, then they can bounce off ideas off each other until termination. Okay. And this would serve to sort of criticize each other. So they will form a society of two agents right now, two agents that will just keep bouncing ideas off each other and reflecting on whether the ideas are correct. So if you have the roles that are complementary, like programmer and stock trader, one knows the market, one knows how to program, you can actually bounce the ideas off and get a functioning trading bot. Okay, whether it earns money, I don't know, but this actually works. Okay, so this idea is used in the paper called Camel. Okay, I'll be talking about it next week as well. This is used in order to do constant reflection amongst two agents. All right. Yeah, sure. I can share the link to the paper as well. Yep. So the same thing for this CEO and CTO is also the paper I'm going to talk about next week. This is the chat dev. They simulated a software company. And so at each stage of the company, they simulate two roles talking to each other like that. And somehow through this simulation, you are able to get like simulate two people discussing, all right? And as long as the roles are complementary, you will get a more productive discussion. So it seems that prompting the agents with different initial behaviors and interacting these agents in certain ways can actually lead to something that is even better than just having one agent itself. Okay, what if we can have more of this? All right, what if we can have more of this? This is just the beginning, right? This is the basics of what can be done. Okay, there can be more ways. So more and more people are talking about systems level approach to large language model. Each large language model agent is equipped with different skills, different tools, different memory, and so on. And they can all be part of like a whole process chain. Like, for example, this one could be text semantic understanding. This agent here could do like image understanding. Another agent might be doing something to do with math understanding. Yep. So you could have very specialized agents, and like maybe at the top here you could have people that do like maybe at the top you can do like stock trading creation. Okay, I'm not a fan of stock trading, by the way, but I use it because there are papers that talk about it. Okay, then another one might be able to do like maybe you are doing a teaching, you're a teacher, and then you want to like come up with ways to like teach stuff. So you can have different hierarchies. Okay, at the more and more top part of the hierarchy, it gets more and more abstract. The task gets more and more vague. Like for example, teach a lesson. All right, then as you go down and more lower, you can actually have more specific things like, okay, what module should I teach? Within this module, what topics should I teach? So this hierarchy is very important because that's more or less how the way we think as well. We group things into hierarchies, and it is kind of not the right way if we only have one level of hierarchy, because that single level of hierarchy will need to do a lot of things. Imagine if you are thinking in the way of like body movements, then you need to control your left leg, right leg, left leg, right leg in order to walk. That's a bit too much planning, right? Too much things at the low level. But if you can go at a higher level, you can say that I want to go from point A to point B, right? Then your agent will then call upon the lower level agents to think, okay, what motor action should I do? So this is a very exciting idea because with this kind of systems level approach, you can solve a lot more complicated stuff. And yeah, you can check out like big words like AutoGPT that tries to do this kind of like goal planning, and then different agents to do different goals. So this is something quite interesting. And I don't think this is the full answer, right? Because you can create this kind of hierarchies. My idea is that these hierarchies actually can be fixed in some ways, okay? Because you don't want it to be too flexible. Too flexible systems takes too long to train. You can already have some level of hierarchy. Like if you are doing a navigation system, your hierarchy can be like city, then you go country, then you go world, you can already fix those levels. And then within those levels, you can let the agents decide what other agents to call and so on. So there is some fixed boundaries that are already predefined. But within those boundaries, I think the agents are free to learn. When do we add in the agents? How do we know how many low-level agents we need? How do we know how many high-level agents we need? Can we add the agents? Can the agents learn on the go? Can we learn new skills? There's a lot of unanswered questions right now. So this presentation, we're going to cover only the basics. I just want you to know that we have not solved this yet. Okay, using agents in real life is difficult. Using agents as a system works well in theory, but in practice, there's a lot of unsolved problems. So I'm going to start on the presentation proper. This is just the rough story overview. And there's a lot of things that we need to find out. Okay, there's a lot of limitations of agents. Okay, right now, they are only limited to very simple tasks because if you do too complicated, there might be hallucination issues. The output is not very consistent sometimes. You can ask it, like in the generative agents paper, the agents can eat breakfast 3 times in a row. Okay, I mean, they don't really have this idea of like you only can do it one time. You need to specifically give the prompt, say you only do that particular action one time, don't repeat. So there are some things that it's not able to do. It's able to associate quite well. So I will talk more about this, like how to let it associate better. So we need to use its strengths, know its limitations, and build the agent architecture, make it more functional. But the idea of agents is a very powerful one because you can use natural language to program a lot of things. And it's quite explainable because you can ask the agent, like, why is it doing something? Right? So maybe I'll just pause here for a minute. If you have anything you want to ask so far about what I've covered so far. Okay, if not, let's move on. All right. So that was, I hope you all enjoyed it. I actually had a fun time creating this, right? So when I thought of agents, I thought of the matrix. And so I created the whole thing about the matrix. So hope you all enjoyed that. All right. So what are agents? So maybe the most apt definition might come from one of the safety engineers of OpenAI. And this is from Lilian Wang. And she says that agents is using large language model as the interface with memory to remember stuff, with some planning skills in order to help it to do more difficult tasks, like things step by step, that kind of stuff, to use in order to overcome some of these limitations like math calculations. So this is more or less what is an agent. I mean, of course, there's a lot more you can think of. I mean, you want to talk about other things like plus systems of agents, plus learning skills, plus learning structure of system. You know, there's a lot of things that we could actually have for agents because an agent itself, okay, might not just be one agent. Okay, I mean, agent itself is one agent, but to make it useful, you might need to have various agents that look at different tiers of the problem in a hierarchy, in a parallel version. So this is something that requires a lot more study. And I think also requires that GPT becomes cheaper. If not, it's going to be very expensive to run it. So this is something that is quite interesting. Let's just see what she proposed in her blog. So this is how the agent looks like. An agent, okay, has firstly some planning stuff like reflection, chain of thought. Okay, self-critic is basically ask the LLM to critic itself in words. Okay, so you don't have to use an RL reward kind of thing. The critic itself can come from the LLM. The LLM can say, oh, you have done this well, done this badly. Okay, you can do sub-goal decomposition like auto GPT. You can split like a big goal, like teaching a lesson into sub-goals, like teach module 1, teach module 2, teach module 3. Right, then you can use tools in order to make it better. Like for example, we showed the calculator tool just now. And we also can augment the agent with some memory so that the agent knows what has been done before and can use this for decision making. And actually, this memory is more or less the focus of my research right now. My learning fast and slow is about augmenting memory to neural networks because I believe memory is the way we learn fast, right? With memory, you don't repeat the mistake twice. I mean, if you can recall that. But like if you, for example, got bitten by a snake once on path A, you are likely not to go back to path A anytime soon because you remember the snake. So with memory, you learn way much more faster than training back propagation of a neural network. Okay, so this part is my primary interest, right? And I think there's a lot more to do with this. Because so far, as you see in the agents architecture, people are just doing memory based on text. Okay, that's not ideal. Okay, because text alone for memory, I will explain later, you miss out on the various levels of hierarchy that you can actually store for this kind of memory. Okay, let's move to the next one. So first about thoughts. Okay, what thoughts can we let the agent do? How do we make the agent think better? So there are some cases where, for example, like math problems, like Mary has 3 balls, John gave Mary 2 marbles. How many marbles does Mary have at the end? No, stuff like this, very tough to actually go directly from input to output. Okay, it's not as simple as, like if let's say like the rain was very heavy today, what was the weather like? Something like this is very obvious because like the answer comes directly like, oh, it was rainy. Okay. So this is very obvious. Okay, this is obvious. Okay, but if you have some problem that is not that obvious, like you take a few steps of inference, like you need to map a certain problem into another type and then to another type, that might be actually difficult to do directly from next token prediction alone. And so people have come up with ways, all right, to get the large language model to try to map it to the right output. And one way is chain of thought, like let's think step by step. Or, okay, this is a method that I like to do as well. Ask it to generate broad stuff first before specific stuff. So like, for example, if you want it to do a 24-hour plan, okay, what you can do is you can ask it to do a broad plan first, then you ask it to do an hourly plan. Okay, the broad plan will cover like what are the things you need to do in the day, and the hourly plan will then build upon that. If you miss out on the broad plan, okay, the hourly plan might be like what happened in generative agents. They eat breakfast 3 times. You know, stuff like that might happen. Okay, so this grounding from very broad to very specific is something that is very important in large language model use, especially for more complicated use cases. Okay, let's think step by step. You know, it doesn't tell the agent, doesn't tell the LM what steps to take. Okay, it's only good if the LM agent has seen examples of this explanation before and can recall it, like recall a scratch pad. They call it scratch pad. Scratch pad is like your inner workings to show like math problems and so on. If you can recall the scratch pad by just doing the let's think step by step, sure. But a lot of real life problems are not math problems like in a textbook. Okay, let's think step by step doesn't work too well for this kind of problems. If you know your domain, you should give it the broad and specific categories of your domain directly. Okay, at least this is what I experienced. I did a few domains already, like medical stuff, and yeah. So this is something that I feel is a lot of hype about this kind of methods. You know, recently DeepMind has a paper. I don't know if you heard of it. It's called Take a Deep Breath and Think Step by Step. Yeah, I have my like skepticism about this because like how much can take a deep breath help you with the problem? Sure, 9 percentage points improvement, but no, it doesn't solve the fundamental issue that you still need to guide the large language model through the different steps. So yeah, there's only so much vagueness you can incorporate like that in your prompt. Okay, it's not a very good way to prompt the LLM. Right. Another thing that I like to talk about is granularity, different levels of hierarchy. There are certain things that are better solved at a higher level, certain things at the lower level. So take, for example, an image. If you want to say an image of a beach, okay, with various people, if you want to say identify that is a beach, you might go at a higher level. Okay, look at the scenery, look at the background. But if you want to say like name like count how many dogs are there, how many humans are there, you might want to go into the object level. Then finally, if you are saying, I want you to reproduce the entire painting again, then you might need to go to the pixel level because you want to remember all the pixels one by one. So this is what I call abstraction spaces. And I'll be talking about like the ARC challenge soon. Okay. This basically I asked it to go into object space, pixel space, and this works way better than just having one generic abstraction space, which is like maybe the grid, the 2D grid for the ARC challenge. So ARC challenge, for those who don't know, is like an IQ test of different colors of pixels. Like for example, if I have a red color pixel here, the input examples might be shift it one to the left. So you need to identify the rule based on the 2 or 3 input sets, okay, the training sets, and then you need to do the rule for the test set. So I find that if we incorporate different abstraction spaces, like it can solve like at least double or triple the number of problems basically, if you can solve a problem with one particular abstraction space, you may not be able to solve for another one. But another abstraction space like object or pixel, you might solve another group of problems. So I believe that there's this kind of hierarchy that's needed. You need to think at different levels and choose the right level for your problem. So this chain of thought thing should apply to different levels of your abstraction spaces as well, not just to one single abstraction space like what is done right now. Okay, so this is something that I'm proposing, right? So you all will hear more about this soon. Any questions so far? Okay, if not, I'm going to go through more about world feedback. Okay, what is world feedback? Large language models are isolated. Okay, you can imagine large language models as like your brain, all right? your brain itself doesn't really have the environment stimuli. Someone needs to tell the brain, okay, you are experiencing pain. You are seeing some object right now. Okay, we don't actually experience the world directly. The large language models do not experience the world directly. You need someone to give some feedback to them to say, okay, this is what happened. You use the calculator 2, you get back the output of 2. You need to tell it that. If not, the large language model has no idea what's going on. If you call a tool, if you like use an external program to do stuff, it has no idea what's going on. So this feedback is very important. How do we incorporate feedback? So early on in the story, I talked about React. Okay, so I'm not going to go through that again. But the idea is, okay, if you look over here, this is chain of thought. You ask the large language model to say, think step by step. Then it will think in terms of like step 1, do this, step 2, do that. Sure, you can do that. Okay. Then you can also ask it, if you need to take actions, you can ask the LLM to say, this is the current context. Okay, the cook is on the table. Okay, I am near the table. What action should I take? So this is like say your robot can go and grab the coke on the table, pass it, go to the human, pass the coke to the human. So you can ask it to plan a series of actions just using the context that you give it in the language model alone. Okay, so this doesn't have like naively doesn't have reasoning. It just asks you to plan a sequence of actions. But if you do React, okay, you can have some form of reasoning. You can ask the robot to think about it like, okay, you need to get the coke to me, all right? What do I need to do? Then the robot can say, like, robot can plan. Okay, to a limiter, you can say that step 1, get coke from table. Step 2, pass coke to me. Go towards user. Step 3, pass coke to user. So with this, you can actually do some form of thought, like, how am I going to achieve this outcome? All right. And then with that thought, all right, you can then ask it to choose a relevant action. After the action is done, the environment will feedback. Okay. So for example, if it tries to take a coke, robot tries to take a coke that is not there. So the feedback can be, environment feedback will be coke is not present. So you can see this environment feedback can act like a critic to the neural network. It can give the neural network some idea, or give the large language model some idea of what's wrong with the action. Or if the action was good, it can say what's right with the action. Right. So this idea of thought, action, observation. Okay, I would like to add one more thing, which is reflection at the end. Okay. This process is very powerful because with this, you can actually do quite complicated things by just this cycle alone. You implement this cycle many times. Okay. Of course, I tried LLM agents before. The action space that you ask it to do must be very simple. Okay, it doesn't do very complicated actions well. Best if you can already tell it like when to use certain actions. Okay, so there are some limitations for this, but overall, this React framework has proven quite successful. I mean, you can even see it being used in the military as well. That's why I talked about the OODA framework, OODA, Observe, Orient, Decide, Act. It's been used quite often. So there's some merit to this way of thinking. And this is really quite exciting because you can then use this LLM agent to interface with the world, use tools interface with the world. It can become a decision-making agent. Can you imagine this done for self-driving cars? I can imagine that. Action space can be turned left and right, accelerate, brake. That's the low-level action space. So let me just write this down here. So like, for example, self-driving cars. The low-level action space will be something like this. Left, right, accelerate, decelerate. What else? Do nothing. Yeah, so this is the low level. The high level could be like go from point A to point B. It could also be like top up fuel. There could be some stuff like that. Okay, top up fuel might be even higher level. Right? Because top up fuel, you need to find out where the location of the fuel station is, then go towards there. Okay, there's some things that are good for language models, some are not. And I would like to tell you why it's not good first, because based on my cooperative 2D escape world, I realized that navigation is not good. LLMs don't do navigations. Okay, best to use like A star search. Okay, why don't LLMs navigate well? Right, because pattern matching unfortunately doesn't come with optimization of routes. Right, it's not like I ask you to go from point A to point B, like look through all the possible routes and come up with the shortest. No, it doesn't really do that. Okay, what would likely happen is that it will just based on what it has seen before and just output something. So yeah, unless you ground it with some memory, which is my learning process. So you ground it with some memory, okay, ask it to run through memory and then like maybe simulate possible futures and find out the shortest one. Maybe it will work. But you know, if you have something that already works well, like A star search, why reinvent the wheel, right? Just use it. Like I believe, those kind of robot vacuums that we have in your house, right? They also don't have large language models to tell them how to navigate. They probably use A star search as well. Yeah, so this is something that is a little different from the brain. The brain doesn't do these algorithms. But I believe since we are programming to AI, we don't have to copy the brain totally. Okay, if there are some efficient algorithms that we already know work, use them. All right, no need to reinvent the wheel. Humans are not perfect. We rely on tools as well. So, yeah, incorporating world feedback like that, okay, and using some rule-based systems or rule-based algorithms that work well. I think these are all quite important things that we can do to make agents quite performant, right? Question so far for this, or anything you want to like talk about? Okay, I'll be moving on then. Right, so there's this paper that has been quite captivating, okay, at least for me also. My strict JSON framework is inspired by this. So Voyager. Voyager is an AI that plays Minecraft. Okay, it plays from scratch. Okay, I wouldn't say from scratch exactly, but it has some basic functions that it has. What are the basic functions? It has like the navigate function. It can go to certain point. It can craft. It can shoot. Okay, because you need to shoot zombies and so on. So it has some functions already predefined for it. What it needs to do is to know when to do those functions. So there are 3 stages of this. One is a curriculum stage, in that the teacher will look at what's available in the world, okay, and come up with certain tasks for the student to learn, right? So this is automatic curriculum, okay, it's able to guide the LLM agent in a more structured manner, such that the LLM agent will learn simple tasks first, then the more complicated stuff, right? Then we also have this thing called the skill library, okay? So imagine all these are your primitive skills, the skills that you start off with. We can actually compose them into more and more complicated skills. Okay? And these complicated skills, where do they come from? They come from if you pass a certain kind of curriculum, your curriculum that you, like for example, mine woodlock. Okay, if you pass it, this will, whatever that you do will be stored in your memory. Okay, and this can be called as a function next time. Okay, what are these kind of functions? These functions are just Python code. In this case, all right, this looks like JavaScript. Okay, so you use whatever language that is needed, okay, in order to like store a function. So this is actually a function as code, skill as code. You basically store the whole code as one skill that you can call later on. All right, so this idea of using code is not new. A lot of people have found out that using code helps you to get more consistent output. Using code helps you to do math better. Yeah, so like using this kind of code to store the skills is one way of doing it. All right, and this idea of generating skills automatically by like composing from the basic one, I quite like this idea a lot. And okay, there's this very important thing I'd like to highlight here. Your actions, okay, is the code, okay? And after a while, the environment will tell you, okay, do you complete the task or not? If you completed the task, great. If you do not complete the task, then they will give you a criticism. Another GPT-4 agent will criticize, will say, okay, you failed at this task, okay, because of what? All right. So even all these primitive skills here, they all have some form of error messages that happen when certain things are done and certain things are not done properly. So all this feedback can be given. Okay, if you have compile error, your environment feedback will be the compile error log. So there's this idea of iteratively improving your generated code using feedback. And that is something quite powerful because with feedback, if you keep doing repeated feedback, you might be able to get better and better code, right? I mean, to a certain limit based on the LLM's capabilities, but you will get better code because it's now grounded to the environment, all right? The environment will give you the feedback, either a compile error or like if the task is not done properly, why the task is not done properly, that will be the feedback they can use to recraft your code again, right? So when I did the ARC challenge, I also used this kind of framework to generate better code to solve the ARC challenge. Okay, so this is something that is quite inspirational for me. Okay. And yeah, world feedback is really quite important. Let's move on to tool use. There's a lot of names for this: tool, function, API, or skill. Okay, so people call it differently, but they all mean about the same things. So how do we do this? Okay, so I mean, I've gotten quite a lot of queries from people like, how do we implement this LLM agents in real life, right? How do we know which tool to use? If you have 100 over tools, like how do we know, right? So one way to do it, okay, this way is the most specific, and like if you really don't want to fail, this way is the best, right? You can just go through each tool, like give it maybe the code of the tool or description of the tool, and then ask the LLM whether is it relevant or not. You can give some form of category. LLMs don't do ratings that well, but if you ask it to group to that particular category, it can do semantic matching to these words here. So you can ask it to rank the tool use, and then you only pick tools that maybe score of 2 or 3, depending on your use case. So that's one way to decide the tools. Okay, another way is that you can have description and use case. So like, for example, you have a calculator tool, the name will be the calculator. The description will be add 2 numbers, and use case use when needing to add numbers. Okay, this, for example, if you want to add the numbers only, you can also do it for other kind of stuff like multiplication as well. So if you give it a description, the LLM is able to use this description in order to do some form of semantic matching to your particular like query. And if it deems that this description matches, it would recommend to call that tool. Use case, I realize is quite important. Okay, because just giving the description alone, okay, it's like telling your kid, okay, the water here is meant for drinking, all right? The food here is meant for eating. Okay, I mean, yes, that is quite good for like describing what's going on, but sometimes LLMs may not be that direct in terms of like, when do I need to eat, when do I need to drink. You might need to tell it like, use case is like, eat this when your energy level is below 4. or like, drink this when your thirst is greater than 5. If you have a particular use case that you need to call that tool for that particular purpose. Like, for example, if you need to add 2 numbers, you can put that in your use case so that whenever you need this kind of use, the LM will know it needs to call this tool. So like, describing the tool itself is like level 1 description. It still requires some intelligence in order to associate what you need to that description. So in order to make things easier for the LLM, you might need to add something like use case so that it's like quite idiot proof. You tell the LLM exactly when is this kind of thing needed. And so this is one of the gripes of LLM agents. Like, LLM agents tool use cannot be too complicated because it's very hard for them to associate if it's too complicated. Best if it's just one step. It's like maybe image generation tool, just one step. Calculator, add 2 numbers, that's it. If your tool like does add 2 numbers, then use these 2 numbers to form some poem, then take this poem and do text generation, do image generation. If that tool use is too complicated, 3 or 4 steps combined into one, good luck. Your large language model agent probably cannot do it. All right, so that's some of the limitations that we have right now. Okay, so I also have some people who have asked me like, hey, if I need to do like something like this, rating every single tool, or like choose the description of every single tool, what if I have 200 over tools, 1,000 tools? How? I cannot fit in the context length. How can I do this? Right, so this is my solution. Okay, if you already know certain tools as different categories, okay, like for example, images, text, okay, you can reference this paper called Hugging GPT because they also did something like that. They take the use case, they group into like certain tags. Then within that tag, okay, they have a very smart way of seeing the Hugging Face stars to see which are the more trustable tools or more popular tools. Yeah, so you can do that to like filter the number of tools you need. So you can do a two-step process. The first step is you can ask the large language model to categorize what kind of tools is needed for that use case. Then within each use case, then you can say, okay, if you want to do images, okay, you can do pics to pics, you can do like I don't know, zoom to you can do stuff like image infilling. Yeah, so within the particular domain of images, you can, if it chooses, okay, I need to do an image tool, you can then give it the description and the use case of all these tools here. So in this way, you reduce the context length. You don't have to give all the tool descriptions. Okay, in my experiments with the ARC challenge, if you give it too many functions to use, like for example, if you give it 20 functions, the chance of it using a wrong function is quite high. Okay, so if you ask it to use only like 5 functions, it's actually much more accurate. So, Claude has like 100 over K context length, this is Claude. Does more context equals better? Likely no. Okay, because if you use too much context, chance of using wrong tool is higher. So it's best if you already can have a meta way to tell the agent, okay, these tools are useful, use only those tools. So yeah, people might think that the LLM agents right now can think like a human, can use the tools like a human, process all this. Reality is not that it cannot do it yet. All right, it requires quite a bit of hand holding. And if you already know like certain categories work, certain categories don't work, you have to filter it before you pass it into the LLM to choose. Right. So yeah, this is some insights I have. Have you all used the LLM agents for tools before? Anyone has like similar insights or anything else to share? Okay. If nothing, I'll move on. Okay, so this is how the chat GPT, visual chat GPT, uses the tools. Okay, so this was a paper I think a few months back. And what they did was something that I liked so much. Okay, there's also another paper called Tool Former, but I didn't really like the way of them doing it because they actually fine-tune in order to get the tools to use. They had to change a bit of the text semantics, add some text for the tool use. Okay, but Visual Chat GPT doesn't need to change your source text at all. What you need to do is just give it a name for the tool, basically the description of the tool, the usage. When do you need to use this? Like for example, when you need an answer about a question based on an image. So this is an image QA tool. The input, the format is like you need one image path and a question and an example. So this example is if you want to do few short prompting. Okay, if you don't need this example, you can do 0 short prompting by just doing this. So I'm not going to repeat the bottom two itself, but the idea is if you give it like the name, the usage, the input output format, okay, you pass it into GPT and then ask it to output like the tool name and the tool inputs in maybe a JSON format. It can output pretty reliably. Okay, so this is I would say this is more or less the leading way of using tools right now. Okay, I like this method a lot. It works. All right, this method works. All right, Ghost in the Minecraft. All right, it's another paper that came out about the same time as Voyager. Okay, talking about Minecraft as well. Okay, in this case, the way they use tools is much better than Voyager. Okay, I like this a lot. I'm working on this right now for the ARC challenge to do tools like this. Okay, what is the difference? Okay, I'm not going to explain all this stuff here. You can check out my video on Ghost in the Minecraft if you want. But the idea is from the context that you give it, okay, with some basic understanding of the tools that are available, in this case, functions. Okay, what we want it to do is to plan out what actions to take. Okay, so it does the React framework kind of thing. Like this is the feedback, environment feedback. Then you have thoughts. Okay, how do you get the diamond? You need to go level 12 and so on. Then you have the actions. Okay, thoughts, actions, and then after that, your observation. So like observation is actually part of the explanation as well. So this is the React framework. But if you take a look at the actions, okay, or the tools that they use, it is not a Python code. It is not a JavaScript code. It is the name of the function and the arguments to the function. That's it. And they basically just take a sequence of actions in the form of a sequence of functions to execute. Okay, why do I like this so much? Okay, because actually in the game like Minecraft, all right, the need for like maybe a for loop is not exactly that needed. You might just need to take actions such as like shoot the zombie, explore this area, that kind of stuff. You may just need to do this kind of high level actions and then let your function do the micro level actions. So if we do this, can you see that the chance of compile error is very low? Because if you just do a sequence of functions with predefined arguments already, right, the chance of it failing is low because for one, the name of the function will always work. Okay, this is part of your action here. The arguments also will always work. Okay, because GPT is able to infer what are the arguments quite well from the context. So if you have all this in place already, okay, the chance of you missing a semicolon, the chance of you like doing an extra for loop or forget to terminate your loop, all this is very low because you have abstracted away your code into a more higher level space. So I like this tool usage format. I put it here because I think this is like the way to go if you can do it something like that. Right, so this is the summary slide for the format. So tool name plus parameters, Visual ChatGPT goes in the Minecraft. All right, you can do it by Python or JavaScript code like Voyager. Okay, I disagree with this format. So I believe Voyager cannot solve quite a bit of problems because it has faced issues with compile error. Right, people might think, okay, Python code, the most generic, or JavaScript code, the most generic, can come out any kind of things. But you know, flexibility with great, okay, I'm going to come up with a quote here, okay, with great flexibility comes a great chance of compile error, of compile error, and also like greater learning curve. All right, if you give it too much flexibility, you need to learn more. Okay, but if you constrain the amount of stuff that you can learn, you learn less, and you can perform better. So this is something that I think in the deep learning world, people are not really touting this because it doesn't sound too sexy. What's sexy is end-to-end learning, right? Like you can do everything flexibly. I don't agree with that. The more flexible you are, the higher the chance of you failing because you need to learn everything. If you already know certain things are fixed, like for example, images maybe on pixel level, object level, you already know that these are the kind of hierarchies that are needed. Why not just put them as part of the structure? All right, so in this case, if your structure allows for this sequential code, if structure allows for sequential code, why not do it that way? Yeah. So food for thought, all right? Tool names plus parameters format is my preferred format for tool calling. Okay, tool learning. Okay, this is something very interesting. This excites me a lot because it makes me think about how humans learn as well. Like you saw earlier that stuff like Voyager, they compose new tools. They create new tools. Okay, I use a different color. They create new tools by composing the earlier tools into a bigger tool. Like for example, craft craft diamond pickaxe is like maybe you craft the earlier axes, you know, that you can chain them together. So like in image, like zoom, maybe if you don't have a zoom tool, you can first crop the center of the image and then you reshape the image. That's one way to do zoom. All right, you basically make the image upscale or downscale it. So there are some stuff that you can combine tools together. And you know, you might be asking me, why do we want to do that? You know, if you can already have your primitive actions earlier, you can just call more and more primitive actions. Okay, the idea is it saves creating meta tools, saves on planning. This is something I would like to emphasize a lot because imagine if you need to like move left leg, move right leg. I ask you to think about move your left leg and right leg every time you walk. Okay, I don't think you'll walk very far, right? Because there's only so much you can plan to walk like that. Okay, but if I give you a new function called move to location, okay, if I give you a function like that and completely abstract away the movement of your left and right leg, you know, you can actually plan more because I can say, I want to move to the fridge to get a drink. I want to move back to the computer here. I want to move to my house. You know, you don't have to think, okay, every time I move, I need to move my left leg and right leg, left leg and right leg. Yeah. You might think that, yes, I can do everything with just moving my left leg and right leg. It will just take forever to plan, right? So if you can have a more meta tool, it saves a lot in planning. And as you know, large language models don't plan that well. So if you can associate everything in one step, your agent will work much better. So tool learning is something very, very useful. Okay, never underestimate tool learning. All right. Right. There's also another school of thought. All right. It's like maybe we can group together the sequence of commonly used tools. So the first one was talking about composing tools into a meta one. It's like maybe based on some code, you know, you call the earlier functions, it become a bigger function. This is Voyager. So the top one is something like Voyager. The bottom one here, you can treat it like Ghost in the Minecraft, where they actually analyze the sequences of moves to solve like 1,000 over problems. And then they, based on these sequences, they come out with tools. Okay, the more the tools that are always used together, they group into one tool. So you can analyze your past tool usage, okay, and propose new tools. Okay, you might even delete unused tools. Okay, so there's always this idea of real estate in the brain, you know, if you don't use it, you lose it. Yeah. So you might you might think that, okay, that's a bad thing. But in terms of like large language models, if you remove some tools, it could be helpful, because if you no longer need those tools, you know, you might call them wrongly. Yeah. So based on past use cases, you might analyze them, come up with new tools, delete old tools. Yeah, this is something that is quite exciting that I haven't explored yet, but this is something that could be explored. Right. So yeah, this is the ghost in the Minecraft was actually the bottom one. Yeah, but I guess you can treat of the bottom and the top as about the same. So this is about how tools can be developed over time. Ghost in the Minecraft didn't do this. They took the tools as fixed. Okay, so Ghost in the Minecraft, they actually got the initial tools like that. This new tools grouping together and like coming out of other tools. This you can say is something that I am thinking about. I don't really see a paper doing that yet. Yeah, but this is something that, like, based on the tool usage, you can analyze certain trends and, you know, make your tools better. Yeah, very exciting area of research, this one. Yeah. All right, next, memory. All right, so we come to the highlight for today. All right, how do we ground the large language model to generate better using what it has learned so far? So I would say this word memory would be one of the most heard words in the next 2 or 3 years, because more breakthroughs in this area will lead to more functional large language model agents. Right, and I'm working on this. So stay tuned. All right. So memory, what is memory? So perhaps the easiest form of memory, the most basic form of memory, is to augment the context. And why do we augment the context? Because when we do self-attention, remember you have query, key, and value. This query comes from like maybe your words in this query part, right? If you don't have this context at the back, okay, what are the keys and values? Okay, the keys and values are just, because we are talking about GPT-like attention, you're actually doing self-attention over the entire context prompt. All right, so if in that context, it contains no information at all about what you need, it kind of needs to remember based on its weights of the GPT model. And that's not going to be very good for a very specific generation. So what can be done is that, for example, you want to ask like, how much is a MacBook Pro? Right? The LM is not going to know how much it is. I mean, it's not specifically trained on Apple's data. And even if it's specifically trained, like the prices change over time. So what you can do is you can search over the product database. So you can say MacBook Pro 13-inch is maybe $4,000. MacBook, then over here you can get MacBook Pro 15-inch is $5,000. It's getting more expensive now. Apple's charging too much. Okay, but anyway, something like this, how do you know what are relevant contexts to retrieve? All right, how? Anyone can tell me? How will we know what context do we augment the large language model from for? You can just type in the chat, like, what do you think will be the most relevant context to augment? Anyone? Okay, you're a little quiet.
Perhaps, I don't know, maybe computers?
Yeah, okay, yes, computers. You can group by category, okay, of this as a computer, and then you extract out based on the labels of computers. Yeah, that's one way of doing it. Right. There's another way of doing it is usually use it's called cosine similarity. So you group all these things into an embedding vector. You can use something like OpenAI embeddings. And then you just based on the embedding vector, which compresses a sentence into one vector, you can then do cosine similarity to see what vectors, like for example, this is the query vector, and like this is the context vector. And if we do cosine similarity, given that OpenAI does the vectors of magnitude 1, all right, cosine similarity is essentially, okay, cosine theta is actually the same as the dot product. Something like that, yeah. So Q dot K, yeah. So it tells you how, based on the cosine similarity, it will tell you how similar the two vectors are in terms of direction. And the idea is that if the direction is similar, you will get similar meaning. Okay. And that's because the magnitudes of all these vectors are all magnitude 1. Okay, by the way OpenAI did it. Right, so cosine similarity has some merit. Okay, helps to find out things that are similar. But because you compress the entire sentence into one single vector, you lose out some information, especially if your context is very long. You know, so maybe not just talk about MacBook Pro. You also talk about like iPads and so on. So you might actually have some meshing up of the context. So yeah. So usually this kind of vector works well if it's like more specific. Yeah, in fact, I find that the way of like if you have this query and then you ask the large language model like based on this query, find out which are relevant contexts. So you can just give it a list of contexts. Context 1, context 2, context 3. So if you ask the large language model to give you the context like that, I find that it works much better than cosine similarity. All right, that's because the cosine similarity, one thing, it loses a lot of information. Secondly, it's trained using contrastive learning, which is a very, very tough way to train, especially when your embeddings have so many dimensions. It's very hard to do contrastive learning. So if you were to do this and preserve the original meaning of all these contexts and ask GPT or ask LLMs to come up with what's relevant, it's much better, but much more costlier. All right, so it depends on your use case. So retrieval augmented generation, very, very widely used now. They call it RAG, RAG, right? And it's good, but it's limited usefulness because sometimes you just retrieve the wrong stuff, all right? So there's also another thing that I would like y'all to think about, okay, not commonly cited in the literature, but you know, that's how our brains work. When we retrieve stuff from memory, do we just retrieve it wholesale or do we modify to fit the current situation? So, you know, people have done experiments whereby like they let you watch a video of a car accident, okay? And the car accident, actually the windows did not shatter, all right? So it's just like maybe one car bump into another. So one thing is they'll ask the participants, they tell the participants, the two cars bumped into one another. What speed do you think the cars, what speed do you think the car was when it collided? So if I use the word bump, maybe you get about like 50, 60 kilometers per hour. If I use the word the car crashed, the average response is about 80 to 90. I can't remember the exact figures, but retrieval of this memory, of this episodic memory, is affected by the words that you use to prompt that memory. So like I give you the word crash, you might think it's faster. Some people also imagine the glass shattered because of the word crash, right? So, and the thing is not just in the retrieval process. After we retrieve, if you remember that the glass crashed, you would think that, hey, actually the video, the glass really crashed. The glass really shattered in that car accident. And then the next few times you think about it, you will keep thinking that the glass has shattered, right? That's why, in CSI, they've stopped interviewing people, like forcing people to recall stuff under very stressful situations, because they find that you can actually make people have false memories in that way. So this is something that looks like a fault in the human memory, right? But what if this is needed for association between, like, to generalize your experiences? Because you think about it, let's say you are living in city A, okay, then you move to city B. All your experiences in city A don't match city B, you see? But what if I can slowly like nudge your memory? So like this is your memory A of city A. What if every time when I recall something to help with my life in city B, I can nudge my memory closer and closer to city B? So if you nudge your memory here, you might make it more relevant. Nudge memory towards current situation, and then make it more relevant. Okay, so this is something that is quite interesting for a cognitive agent to have. When you recall the memory, you change it, and then you store the changed memory. That might be useful for adaptation. It's not so much useful if you are like creating a store to help people purchase stuff. You don't want to change your context, right? You don't want to change the MacBook Pro price as 4,000 or 15-inch as 5,000. But if you're like an agent trying to explore the world, sometimes maybe nudging your memory towards something more useful might actually help you perform better. So, food for thought. All right, I don't think many people have done this. So it's something that I was thinking about recently. And yeah, if you're interested to talk more, we can talk more about this separately. All right, so this is memory so far. We do have other forms of memory, as what I mentioned earlier. We have the short-term memory, which is like the conversation history. Long-term summarize. Relevance-based is like retrieval augmented generation. You retrieve the past conversation. But there's a big problem of memory right now, is that everything is based on text. All right. And if you just base everything based on the text input, sometimes like you might have like higher level planning, like for example, you walk left, walk right, walk left, walk right, your feet, you might reflect and say, I move from point A to point B. But if you think of everything as your input domain only, you lose out on these levels of abstraction that you have when you actually perform the action, and then you gain some insights at the higher scales. All right. So my idea is that we should not just only retrieve memory at the lowest possible level, which is at the input level. We should also retrieve memory at all the multiple levels of hierarchy that we are processing the model at. Okay, that means in the transformer, you retrieve memory using similarity maybe at the second layer, third layer, fourth layer, and so on. Okay. All right, so another interesting thing about memory is that you can perhaps use it to improve your performance. And how? How is that possible? So one way is to just say what has worked and what has not worked for a particular environment. So you can say that, oh, mining, making the crafting table has worked, making diamond pickaxe has not worked. So essentially you are trying to give some categories for the large language model, and the LM will try to do what has worked more. All right. So one example of this is like the automatic curriculum in Voyager. They use this method to say what has worked, what has not worked. So it's to tell the agent, give me more curriculum that actually is suitable for me. Right? Recently, the prompt-based optimizer by DeepMind, the one that say take a deep breath and think step by step, that is also similar. They give the prompts and the score, and then they ask the LLM to optimize the score. Okay, I don't agree with the approach, because I don't think LLMs are great optimizers. Right? It just learns how to associate, but optimizing stuff, that's not the right architecture to use. Okay, but this optimizer is sort of something like what has worked, what has not worked. That's why I see the prompt is take a deep breath and think step by step, because they actually gave think step by step as one of the what has worked, So this is something that can be done using past experiences to try to improve the model. But there's a caveat here. It can only improve the model if the LLM can generate it. Okay, if the LLM cannot think of that kind of response, there's almost no way your past experience can ground it to make it better. Right? If like your large language model cannot do differentiation, okay, what has worked and what has not worked, I can tell you what has not worked is differentiation. What has worked is maybe like addition. It's just almost impossible for the large language model to suddenly be able to do a skill that it has no experience of doing just from what has worked and what has not worked. So there's a limit to what you can do with this. But if it can do something and it just needs to activate that inner skill, then you can do this. You can condition it on what has worked and what has not worked to try to generate stuff. Okay, the next thing is knowledge graphs. So knowledge graphs can actually be useful for memory as well. So I think this is something that needs to be explored more. You can select the right level of the graph relevant to the query. So, I always believe you think in multiple levels of abstraction. So for example, if you want to find out like, okay, where should I sit? So you look at here, you look at the bottom level hierarchy. But if I want to find out more like, okay, which area should I go to? Then you look at this level of hierarchy. All right. So when you look at this level hierarchy, you can just extract out everything below it. So this can be your context. So when you go at that level hierarchy, everything below will be your context. And of course, you can also say that, oh, I want to decide which house to go into. Then you can go here, and then everything below can be your context. Okay. So this idea of knowing where to get the context from, if you express your information in the form of knowledge graph, and in knowledge graph actually mean a hierarchical graph, okay? Because to me, hierarchies are very useful ways of representing knowledge. You can actually use this to condition certain things. Like over here, you can condition the Ming Ming's house, and then you can use that to generate stuff. Okay, so different levels can be provided as different contexts. When I talk about chain of thought prompting, this is exactly chain of thought prompting. You ask it to think step by step. It's actually asking you to go from top level, you go one step down, this is one step, and then you go another level, you go another step down. So think step by step helps to do this in a very vague way. So that's why I say if you can prompt it from broad to specific stuff, you don't have to use the thing step by step. You can just say, which house should I go to? That's level 1. And which room should I go in the house? That's level 2. Which object should I sit on in that room? That's level 3. So in fact, we may not want to plan all 3 levels at one time. We might want to plan at the house level first. Okay, so you can give it, like, for example, your input space will be like this: Ming Ming's house, John's house. So you can say, like, which house should I go? Like, I need to do task A. Which house should I go? Right? Then next, I have the next level is like that. Like input will be study room, kitchen. Like I am in Ming Ming's house. I need to do task A. Which room should I go? Yeah. So you can see that this is like the next level. Let me just put this somewhere. You can prompt it with the available actions at each level and have the meta context being passed through all the way from top to bottom. Okay, that's what I mean when like you pass all the context down. It may not be all in one prompt. It might be iteratively prompting from broad to specific. And this is what is used in the generative agents paper. When they ask the agents to decide where to go, right? They actually use the world represented as a JSON, right? They ask it like, okay, like what I'm talking about, which house, which room, which object. So this is done in the generative agents paper. Okay, go check it out. Generative agents is one of the best papers I've read. All right, so this idea of prompting from broad to specific is already inbuilt inside this architecture. And this idea of representing the world as a hierarchy is already there as well. So the idea of this knowledge graph, building the hierarchy, very, very important. Okay, very, very important. And knowledge graphs can also serve as a way for us to build upon more levels of hierarchy. Like for example, in this study room, I saw another thing. I saw an alarm clock. So I can then add on my knowledge here. I don't have to start from scratch to add on this alarm clock. I already know. I've seen a study room in my memory. I can just put this new object alarm clock inside the study room. Okay, and the next few times I retrieve stuff about the study room, I will retrieve the alarm clock as well. So this is a way to build a dynamic knowledge graph. It's not a fixed knowledge graph. It builds as the agents experience the world. So something that is very useful, not very well used. Okay, because everyone's doing retrieval augmented generation. This is not a good way to do it. Okay, I think in time to come, this will be the lousiest method. All right, but this is the best method now. This is the way to go. Knowledge graphs and large language models. This is the way to go. Okay, let me see how many more slides I have. Okay, I think I need about half an hour to cover the rest. Are y'all okay with another half an hour? If not, I will continue next week. Maybe we get a show of hands. Are y'all okay to stay another half an hour? If not, we will split this session up into for next week. Okay, no problem. If you have to go, I will record this and upload this as well. Okay, then don't mind, I'll overshoot a bit because I think I have quite a lot to talk. All right, so we will do another half an hour. Is that all right? Okay, so this idea of multi-agent systems is what I talked about earlier. Okay, something that I'm a big fan of, because as a single agent, you are only able to do certain things. But with more agents, you are able to do much more things, much greater things. Okay, and this is something that I think is very useful. So for example, before we talk about the multiple agents, okay, we talk about the benefits and drawbacks of these agents first. Okay, what are the benefits? The benefits is that we do have a flexible way of doing it. We have a flexible input-output. Okay, so using large language models, okay, as agents, what are the benefits and what are the drawbacks? The benefits is that you get this flexible input-output. You are able to do any form of input and then process it because it's just next token processing. There's no like limitations to your input, apart from the fact that it should be one of the recognized tokens. You're able to pattern match the semantics. You're able to retrieve the information in the specified formats well. Like in JSON, you can get the output well. And you are able to customize your large language model to new tasks easily by doing this zero-shot and few-shot prompting. Okay, so this is something that I think is quite interesting, because with large language models, you can do all this, right? But what are the drawbacks? The drawbacks is that you may not be giving consistent output. You may not give the right kind of output. Right? You may not be able to follow the rules well, okay, like rule-based systems. And it also takes quite a long while to generate tokens, can be quite costly. So I think in this multi-agent framework, you need both. You need both large language models and you need rule-based, right? Because in order to do that, okay, with this tool, you can then program a hybrid kind of solution that can utilize both the benefits and the drawbacks of both models or both approaches. So this is the system level approach to large language model. I think you all saw this earlier with the robot slide. So you have different levels of hierarchy, talking about different views of the problem. And then at each level of hierarchy, you actually have some people under you, all right, to actually execute this out. So this is something that, this hierarchy is something very useful because you can use a very complicated top level hierarchy. Like for example, top up fuel for the car, complicated problem. You can then break down the problem into find out current location of car, find out location of nearest fuel, the petrol station. And then after that, you can then do the navigation. So you can do this breaking down into subparts in the hierarchy quite easily. Each subpart can be solved easily, more easily, all right? So this is like auto GPT. And this is the interesting thing. Everyone's talking about LLMs right now, but you know, sometimes the solver can be both an LLM and a rule-based system, or like either or combined. Like for navigation, why do we need to use LLMs, right? Let's use A-star search. Okay, A-star search works much better. Okay, you don't have the problem of like not being able to associate the correct location. Like stuff like, in general, stuff like optimization are better done using rule-based, okay? Because LLMs don't do that well for optimization. So if we can allocate this part to the rule-based system, you use the LLMs for what it's good at, association, pattern matching. Use rule-based for what it's good at, consistency, to optimize stuff. Yeah, you do both combined together. Your solver will be very powerful. Okay, use both LLM and rule-based. And this part is also important at the back. You can use rule-based ways to check whether the solution is correct. So like if you already know that like you need X and Y in the solution, okay, what you can do is you can reject anything that does not contain it and use this to prompt solver for the solution. So like if you already know that in order to go from point A to point B, I need to pass by the coffee shop, and the coffee shop is not in a route, you can prompt the solver, hey, you need to include this coffee shop. So this idea of iterative prompting, okay, with the error messages, this part is also quite important. So the solver is not just a one-step solver, it's an iterative feedback loop that keeps going and going until you solve the problem. So this is the idea of like breaking down problem in subparts. Let's now talk about AutoGPT. There's a very similar approach. It's called Baby AGI. You actually have the agent like take a task from a task list. Okay, you have execution agent to see like how to execute it. Okay, context agent is just refine the context to the particular use case. Okay, so this thing is that after you execute a task, then you need to see whether you need to create more tasks, which task to do next. So the idea of creating new tasks, new subtasks to solve problems, this is something that is quite inherent in like a hierarchy. Although the problem with this baby AGI, let me just put here problems with baby AGI and AutoGPT, there's actually some problems with this. The problem is that the hierarchy is not defined and left to LLM to infer. So problem, this may not be the best way to do it. Okay, if you can actually have the hierarchy that you really want, like for example, top level hierarchies, broad view, then you give some example of broad view is like general description of the solution, then like level 2 will be like the more specific details of the solution. So you like prompt it to think in terms of hierarchy from top to bottom, give it some examples, then maybe the task that it creates will be more, or the sub goals that it creates for AutoGPT will be more aligned to this idea of hierarchy. And, you know, maybe that's the way to solve it, to make it better. So like stuff like asking LLMs to think of their own goals, you know, that may not be the best way to do it. Yeah. Yeah. So this hierarchy thing needs to be more cutthroat. It needs to be more defined and implemented in the system for it to work better. All right. Any questions so far for this? All good? Okay, so next we talk about the community of agents. So we have this community of agents that I talked about earlier. Each of them have different initial contexts, interact with one another to achieve a goal. So like generative agents, you know, the Sims, they talk in a Sims-like environment, they interact with one another. One wants to do a Valentine's Day party, and then like it spreads around everyone. So yeah, this is quite cool because like you can see the different characters of the agents can be just prompted with like you are store owner, you do this. Yeah, you know, something like that already gives the context. So I can totally imagine in the future like RPG games, you can just use text to prompt your NPC, non-playable characters, and then you can interact with these characters that respond to you in different ways. I mean, I've done games like the lawyer game and stuff. I totally believe this is possible. As long as that kind of character is widely available on the internet, definitely you can do this kind of stuff. You can just give some zero shot description of like what to behave, how to behave, and the agents can do things differently. Right? Chat dev, you can just say you are the CEO of the company, or you are the CTO, or you're the programmer, you know, that you will magically get the relevant skill sets needed. So that's quite interesting. Like even if you do stuff like, I mean, not just for LLMs, you do stuff like image generation, you use Mid Journey. If you just say that, okay, I want your expression to be cute, I want the expression to be realistic, like just one word like that, you can already like give a different kind of image. So this initial contexting is quite interesting for generative models because it can condition how the model behaves. And you can use this in the community of agents to simulate different roles. Because sometimes you get intelligence by an ant colony. You have different ants doing different things. If you specify different roles already, as a group, the group of ants can do something bigger than what an individual ant can do. So similarly, a group of agents with different initial conditions can actually perform better. And each agent can have their own particular expertise that they can solve their problem. They can have their own memories, their own tools. Remember I said, don't spam the tools. You put too many tools in one agent, it underperforms. Each specialized agent with a different set of tools can be much better. Okay, not only does it fit the context length better, it also hallucinates less. Right? So this idea of community of agents, very, very powerful one. And this idea of collective intelligence like the ants, very powerful also. You can have agents not just with various roles, but various hierarchies. Some agents look at the more meta level actions like go to point A, go to point B. And the agents at the bottom look at like, okay, move up, move down, move left, move right on the grid world. Okay, this is like my 2D escape room that I talked about in one of my earlier sessions. So I found that this approach of hierarchy solves the problem way faster, way better than if you don't have this. All right, you can pass the problems up and down the hierarchy. So I talk a lot about hierarchy, different abstraction spaces. Actually, they're all the same because I believe the abstraction spaces are all tied to hierarchy. Right now, deep learning is only doing bottom level hierarchy. Like large language models, more or less is bottom level hierarchy. If you can have these layers of hierarchy, I believe the solution will be much better. Okay, then you can also pass the problems up and down the hierarchy because not all problems need to be solved at the higher level. Like if I want to navigate from point A to point B, I should be at a higher level. But if my problem is about how to move my leg up, I should go to the lower level. I should go to my leg muscles. I shouldn't be thinking about navigation. So different problems call for different abstraction spaces, different hierarchical spaces to solve it. So this is something that I think needs to be implemented for the future systems. Challenges. All right, so you all hear me talk all the good stuff about LLM agents so far. Why are they not used yet? Maybe before I talk about challenges, if you all have done LLMs before, can you all type in the chat or something like, why do you think LLM agents have problems? What are some of the challenges that you think we face? Maybe I give you all about 1 minute. Just whatever grievances you have, just put in the chat. I'm quite interested to hear, like, if you have tried this out before, like, what problems do you all face? Okay, I'll just start talking first. So one of the challenges for implementing agents is the finite context length. So with finite context length, you cannot put too much in the context, okay, unless you do fine-tuning. So there are papers that try to do usage of 200 over 2s by fine-tuning. Is that a good idea? Okay, my instinct tells me it's not a good idea to fine-tune to use 2s because when you fine-tune like that, all right, you can't change your 2s anymore. When you okay, so this is the thing that I need to talk about, general and specific models right now. So if you have general models like this, let me just put here general models, okay, and then when you fine tune, you get specific models. You fine tune over here. When you fine tune a general model to a specific model, you lose out on the generalizability, but gain on the specific use case. So if you fine tune with tools, okay, you'll be quite good at using those tools you fine tune for the particular examples that you fine tune for, right? But because you don't give it the context of like when to use certain tools, it's no longer able to like zero-shot generalize to other use cases for that tool. So you better make sure your training examples cover almost everything of how the tool will be used, right? So fine-tuning, I think, might solve if you have a very specific use case you want to do and you don't really care about expanding beyond whatever you fine-tune on the examples. Sure, you can use fine-tuning, but if you want it to be more generic, fine-tuning, I don't think is the right way to do like tool use, okay? But fine-tuning for like specific data processing, sure, we can do that. For tool usage, I don't recommend it. Okay. One way I recommend is to split the prompts up into smaller chunks. Okay, so you can have specialized agents with limited tools. This one I recommend because you still keep the idea of having flexibility to use tools in new scenarios, and you also mitigate the chance of hallucination if you use a more constrained agent. So I'm an advocate of this method. Okay. So next we have problems in long-term planning. So what are the problems? LLMs can do pattern matching in a suitable abstraction space, but may not be able to do long-term planning. Okay, this is what I mean by like when you associate, only good when it's one step. Okay, two step may have some problems already. Like if the association is a direct one-step association, LLMs can do very well. That's why in the ARC challenge, like if you give it object space where you can see all the objects, and the problem is about changing some attributes of the objects, it can do the pattern matching quite well in that space. Okay, but it will lose out in like, it cannot do the pixel level manipulation, like change one pixel. It's not that great at doing that. Okay, because it's the wrong abstraction space. So LLMs needs to be done in multiple levels of abstractions in order to solve various different problems. Okay, and with these various levels of abstraction, you might be able to mitigate some problems with long-term planning. Because if your abstraction covers actions over a long horizon, it is like long-term planning. Okay, so this one a little hard to see, but the idea is if your actions are broad enough, like move from point A to B, it's as though I plan my left and right leg movement all the way until from point A to point B. It's as though that happens. But in reality, I'm just choosing something of a higher plane, right? You do realize that for us, like in the human brain, we don't actually do long-term planning that deliberate, that often, right? Because it consumes a lot of brain energy to plan step by step what will happen, right? That's why playing chess is difficult for us because we need to imagine all the possibilities of the different moves. It consumes a lot of brain energy, right? So if we're able to plan in different abstraction spaces, you might be able to match the high level action. And that high level action is sort of a plan already. So that's the beauty of using abstraction spaces. Okay, so this idea is like what I talked about earlier. You can reduce planning steps. Like for example, this hierarchical navigable small worlds, you start finding the nearest. This is actually about finding like nearest neighbors. You start finding nearest neighbors at the highest vector. Basically, they have different vector lengths at different levels of hierarchy. You start from the largest, and then you move on to the smaller and smaller ones. So I'm going to talk about this soon because I quite like this idea of hierarchy. So hierarchical navigable small worlds. I just came across this idea, and I like it quite a bit, right? My work, okay, you can also use this thing called simulate multiple simulations. So my belief is that, the brain doesn't purposely plan to do something. We have different multiple mini columns in the brain, in the neocortex. Each mini column, my hypothesis is that you might be able to do some form of simulation. You simulate a possible trajectory out, and then at the end, all this will compete with each other, and we will vote for the trajectory that is the shortest or the most optimal, maybe, or the best trajectory based on certain factors. So you can simulate and filter. So I term this simulate and filter. So like you only take in trajectories that fulfill certain conditions, like reach the goal state or like use a certain object, So this multiple simulation and filtering, I believe, is actually the basis of intelligence. So you can check out this paper called Alpha Code. They also like generate different codes, and then they just filter based on whether it can solve the training set or the example test case. So this is something that excites me. So intelligence is not just going through one time, it's doing multiple parallel simulations and choosing the best one. So that's probably how we get optimization as well, because we get the best out of what we simulate. It is not optimal, but it is good enough. Because if I give you like 10 possibilities, I ask you to choose the best one, the chances are you won't get something too bad. All right, because like the more you simulate, the higher chance of getting something good. Okay, I think the most relevant example is in gacha games. Yeah, I don't know if you all play gacha games. Genshin Impact maybe. Like if you draw a card multiple times or draw a character or gear multiple times, the chance of you getting a good gear is higher, right? Like so the more you repeat, okay, even the chance of a good path maybe is like 1%. If you draw it 10,000 times, more or less you will get the good path, okay, eventually. So the idea of using multiple simulations to get better outcomes, and then you can use that better outcome to then train like the agent to continue doing the outcome. Yeah, the idea is quite interesting. So more details, if you all haven't already, you can check out Learning Fast and Slow. Yeah, I'm going to present it at ICDL in November. Yeah, so finally got accepted. Yeah, it took 1 year to get accepted. So yeah, quite happy about this. My next 10 years will be building on this idea. So you can catch more about how I integrate LLMs into this and knowledge graphs as well into Learning Fast and Slow. All right, the other challenges of implementing agents. Agents may keep calling tools when not required. Okay, so this is one of the problems. They are very trigger happy. They like to keep using tools. So in Auto GPT, they even had this thing called a tool that does nothing. So it's like a nothing tool. Okay, I personally think this is not a good way of doing it, because like if it doesn't need to use a tool, you shouldn't just ask it to use a tool called nothing. All right, there must be something that tells it at a higher level. You know, you should only use tools when required. Okay, a nothing tool is just a way to bypass the system, but it just means that something fundamental is lacking. All right. Formatting errors. So output code will often result in compile error. How about a level of code that is more abstract, like a sequence of functions, like what goes in the machine is doing? So this is what I'm working on for the ARC challenge as well, a more consistent format for code. So if we want to use like code as tools, all right, or as skills, I believe that using the naive Python or JavaScript code is not a good approach. But rather, if you can make the code a bit more consistent for your use case, a more abstract format for your use case, I think that is better. Okay, so these are just some of the challenges of implementing agents so far. I think overall agents are a great way. Using LLMs are a great way to understand how an agent interacts with the world. All right, and it provides us with a very flexible way to interface the agents to use tools to solve various problems. But there are still problems with using agents at the moment, and most of it comes with like when to use the tools, like how to plan, because large language models don't plan that well. All right, so how do we resolve all this? Once we resolve all this, we will get a better agent. All right, and so all these are actually some preliminaries about what agents are and what are some of the challenges. Hope it's been interesting for everyone. And now I'd like to invite everyone for some discussion. Okay, this questions to ponder. Usually I do this every session. So I'm going to go through the questions, and then if you have anything else you want to add, just feel free to just sound out or talk in the chat. Okay, so I'll spend the next 5 to 10 minutes talking about questions to ponder. So first, okay, multimodality. Right now we talk about text. How can we incorporate other modalities into an agent? Okay, so one way to do it is like visual chat GPT. Okay, you basically convert the interactions with other modalities into text. Okay, so like you ask and use tools for other modalities. Like for image, you use image processing tools. For audio, you use audio processing tools. But eventually, when you talk to the LLM agent, you talk everything in text. Okay, that's one way of doing it. The other way is you train a multimodal LLM, where basically you have tokens that are of different modalities. Okay, some issues with this is that you need a lot of tokens. You need different tokens, and this may be hard to train. So if you have the resources, yes, you can do that as well. Any other inputs? So I think these are mainly the two ways. One is to process everything as text and use tools. The other way is to inbuild the multimodality inside the agent itself, but you need to train over lots of examples in order to train the multimodal large language model. Yeah, so I mean, some examples of multimodal large language model are Blip, some question answering. There's also another one called Lava that does vision processing using the Llama model. Okay, next, how can we better use memory? So this part here, I answered a little bit in the earlier slides. One way is to do memory at different abstraction spaces. Maybe you also need to have a memory that is stored in a hierarchical way, like knowledge graphs. You also might need this thing like memory that changes according to context to make it more relevant. So this is like the way that our memories can change when we retrieve it. All right. Next, how are the initial tools learned? Okay, how are the initial tools and skills learned? This one, I believe that you come inbuilt with basic tools. Okay, like a baby, like for example, walk, run, or like basically muscle movements. All right, I mean, at least for humans, this is the basic tools. For other applications, maybe like cropping of image and so on. Yeah, then you learn how to combine tools together. Okay, so actually the combination of tools might happen at higher levels of abstractions. So when you combine the tools together, you need not like include this tool at that current level of hierarchy. When you combine the tools together, that tool might be a tool for the next level of hierarchy at the top. So I think this is one way of learning tools. I had to think more about this, something that I'm thinking actively right now. I don't have the answer for this. If you have some idea, feel free to chat with me on this because I'm quite interested as to how we can learn these skills. Okay, right now the tools and skills are more or less self-defined at the start, like the navigation tool, like Visual Chat GPT, the visual foundation models are all given. There's no learning here. Okay, maybe the only thing that has learning that I've seen so far is like Voyager, where you learn the skills by composing earlier skills. Okay, but even for Voyager, it comes with the problem of compile error, you might compose wrongly and so on. So we haven't quite solved how to learn skills yet. So this is something that I think will be interesting. Yeah. I'm more of the opinion that if you can compose your skills in a sequential way to form meta skills in that same sequence, maybe that's the way to do it. Still thinking about it, but yeah, happy to hear your comments on this. How do we determine when to generate these new tools and skills? I think this is based on the query, based on the context, or based on your experience. If need to, if you find that you keep doing same sequence of actions, can make it a meta action. Yeah, so maybe this can be done like as a way of reflection, maybe added or removed with reflection. You can have these tools be added. If you keep using them, like past a certain threshold, you will add that into your database. And maybe if a skill is not used after some threshold as well, it will be removed from your database as well. Okay, last question. When should rule-based systems be used? And when should LLMs be used? So I think I answered this question earlier, like rule-based will be more for consistency, optimization, LLMs for flexibility, and if you need association. So in the agents framework that I'm thinking of, the multi-agent one, is not just LLMs as your agents. LLMs can interact with tools that are more rule-based, for example, or it can have a way to do the checking of the output of your agent in a more rule-based fashion, so as to make sure that it adheres to certain guidelines. All right, like if you want it to reference certain sources, to cite certain sources, maybe you can use a rule-based method, or you can just use another LLM to make sure that the sources it cites are accurate. Something like that. So you should combine both of them together, use each one for its strengths. Okay, and that's all for today's session. I hope it has been interesting. I mean, I actually enjoyed quite a lot preparing for this. So yeah, maybe one last minute if you all want to ask anything. Okay, if not, thanks for coming, and yeah, I'll see you all next time. Okay, bye, Ren.